In this part of the Computational Intelligence course related to fuzzy systems, we will continue fuzzy set theory. We will consider three-valued logic in which half is also considered as a truth value beside true and false. We will try to understand how and or implication and by implication operations are defined in three-valued logic by Lukasiewicz, Bower and others at the beginning of 1930s. And then we will see how the three-valued logic is extended to multi-valued logic. At the end, we will see the definition of not and or operations on fuzzy systems in terms of membership functions. These definitions were proposed by Zadeh in 1965. The basic principle of classical logic is dependent on principle of bivalence. This is saying that every proposition is either true or false. It has been formally developed by Tarski. Lukasiewicz suggested to replace it by the principle of valence. Every proposition has a truth value. Propositions can have intermediate truth value expressed by a number from the unit interval 0, 1. Aristotle introduced a logic of terms and drawing conclusions from two premises. The Greeks, Chrysippus, also developed logic of propositions. Jan Lukasiewicz founded the multi-valued logic. The multi-valued logic is to fuzzy set theory, what classical logic is to set theory. A two-valued logic can be extended to a three-valued logic in several ways. That is, different three-valued logics have been well established. Truth, falsity, indeterminacy are denoted by 1, 0, and 1/2, respectively. The negation, not A, is defined as 1 minus A. Therefore, the complement of 1, not 1 is 0, not 0 is 1, and not half is half. Other primitives, for example, and or implication, by implication, differ from logic to logic. 5 well-known three-valued logics named after their originators are defined in the following. Consider all possible combinations of the values of A and B. We have 0, 0, 0, half, 0, 1, half 0, half, half, half 1, 1, 0, 1 half, and 1, 1. For each one, we have 3 different values. So, as a result, we have 9 different combinations. By Lukasiewicz, AND operation is defined as the minimum of A and B. So the minimum of 0, 0 is 0, 0, half is 0, 0, 1 is 0, half 0 is 0, half and half is half, and it is defined in this way. Minimum of 1 and 1 is 1. Minimum of 1 and half is half, this way, and the value of the AND operation is defined. OR operation is defined as the maximum of A and B, and for example, here the maximum is 1/2, and here it is 1, and at this point it is 1, etc. For the implication, minimum of 1 and 1 plus B minus A is used. So for each combination, calculate this value, and it is written here. For the by implication, 1 minus absolute value of a minus b is used. So in this way, by implication is calculated. And we have other three-valued logics defined by Ugur, Kleene, Hayden, Reichenbach. And notice that the results are sometimes different when we have the value half as the value of A or B. But for the other parts, when A and B are either 0 or 1, in these cases, the result of the operations are the same for any of the logic mentioned here. All of them fully conform the usual definitions for A and B element of 0, 1. They differ from each other only in their treatment of half. The question is, do they satisfy the law of contradiction? That is, A and not A is equal to 0, and the law of excluded middle, that is, A or not A is equal to 1. Check for all these if these are true or not. After three-valued logics, we can generalize that to n-valued logics for arbitrary number of truth values for n greater equal to 2. In the 1930s, various n-valued logics were developed. Usually, truth values are assigned by rational numbers in the interval 0, 1. The key idea is uniformly divide the interval 0, 1 into n truth values. The set Tn of truth values of an n-valued logic is defined as, here we have the logic values, 0, which is equal to 0 divided by n minus 1, and then comes 1 divided by n minus 1, 2 divided by n minus 1, up to n minus 2 divided by n minus 1, and n minus 1 divided by n minus 1, which is equal to 1. These values can be interpreted as degree of truth. Lukasiewicz proposed first series of n-valued logics for n greater equal to 2. In the early 1930s, he simply generalized his three-valued logic. It uses truth values in Tn and defines primitives as follows. Not A is defined as 1 minus A and B is defined as minimum of A and B, A or B is defined as maximum of A and B. The implication A implies B, the minimum of 1, and 1 minus B minus A is used as a definition of implication. And for the by implication, 1 minus absolute value of A minus B is used. The n-valued logic of Lukasiewicz is noted by Ln. The sequence L2, L3 up to L infinity contains the classical two-valued logic L2, this one, and an infinite-valued logic L infinity, rational countable values T infinity. The infinite-valued logic L1, standard Lukasiewicz logic, is the logic with all real numbers in interval 0, 1. Here 1 is the cardinality of continuum. Zadeh's fuzzy logic proposal was much simpler. In 1965, he proposed a logic with values in interval 0, 1. Not A is defined as 1 minus A and B as minimum of A and B, and A or B as maximum of A and B. The set operators are defined pointwise as follows for mu and mu prime. Not mu is a function from x to x, and not mu x is defined as 1 minus the membership value of x. The AND operation on membership functions mu and mu prime is a function from x to x, and if we apply mu and mu prime on x, we take the minimum value of the membership mu and membership mu prime on the point x. For the OR operation, again, this is a function from x to x. The OR operation on fuzzy sets at a point x is defined as the maximum of the membership of x in mu and membership in mu prime. For example, consider this fuzzy set, this triangle, then complement is 1 minus the membership value of the fuzzy set. So up to this point, the membership value is 0. So it has value 1, the complement has value 1. Then it goes to 0. It is 0 at this point. And then again increases by constant 1 minus the membership value. And after this point, it has value 1. This is the fuzzy complement. Now consider two fuzzy sets. This one, suppose that this is mu, for example. This is the mu prime. As the intersection and operation, we use the minimum of the membership values. So at any point, consider the membership value. For example, here the membership for the mu prime is 0, and whatever is shown here is the membership value for mu. And up to this point, 0 is the minimum. And then up to here, we are following this line. We are always taking the minimum of these two memberships. Up to this point, it is 1, and then it becomes 0 here, and it continues as 0. As the union of these two sets, two fuzzy sets, we are taking the maximum of the values. So up to this point, mu is greater than mu prime, so it's following mu. And it goes as 1 up to this point. And after this point, after this x value, the membership in mu prime is larger. So it is following the second set, and it goes to 0 at this point. So this is the union of the fuzzy sets.